Yeah, so hello and welcome to another After Hours. This is for hash tables. Okay, so yeah, we're just gonna go over um, the hash table implementation first, um, and then Victor is gonna proceed with some challenges. Okay, so let me go ahead and share my screen here. Um, okay, and let me go here to this. Okay. Um, I already have the code written down because just to save time, right? But I'll go through it, and if you see anything you don't understand, just interrupt me. Okay. So just like a general idea of what hash tables are, right? We have a pretty cool website here to see it. So I'll post it here in the After Hours channel for you. And basically, for example, if I insert something with what's going on here, it doesn't let me type. How interesting. Yeah. Well, that's unfortunate. Oh, yeah, never mind. It was my fault. So if you go into strings, right, and you try to insert one key into your hash table, it's gonna hash it first, right? As you can see here, like it's doing, I believe it's FNV1. I'm not sure, but I think it is. Might be DJV2, but yeah. Either way, it's hashing based on what I typed in. And then, yeah, it turns out that it gave the number 12. That was the result of the hash. So it was placed here. Okay. And I don't know, maybe if I add another door, it will go to the same place. Let me speed this up. Right. So now we have two of them in the same index, but because there's a linked list here, we can store multiple values. Okay. Everything making sense so far? So a hash table is just an array, and you can store directly the values that you want there, or you can store a linked list, which will allow you to handle collisions. And what the collision is as you just saw, is where two different things give you the same index number, and then they go to the same spot, right? All right. All good. So yeah, I guess if I added more stuff, I don't know if they're gonna collide or not, because this is pretty, it really depends on the hash, but we'll see. Okay. So basically, if I had like something with a lot of letters, it takes longer to hash, and it will always go within the range of these indexes. Okay, so turns out that this one made a collision with cats, right? If we weren't using linked lists, then it would replace it and we would lose data, right? But with the linked list, we can store all of the values, right? So I don't know if there's any questions so far. Josiah, yes, you can speak, you can unmute, you can ask questions directly, or you can send them in chat, all right?
Okay, I have a question.
Yeah.
Um, from the browser, I can see that it's hashing only in FMV1. That's what I can see from browser.
Yeah.
So I don't know, is that the only method of hashing?
Um,
Because I know that there's JB2. So
yeah,
what can
there is
what
DGB2 as well.
FMV?
Sorry, what
Sorry,
was the
please.
Sorry,
How did
question?
you know it is FMV1?
because this is because of those how do I put it? The zeros, multiple zeros, it keeps on repeating. Because I Google searched it and I noticed that FMV1 always appear this way, and it's kind of like different from the way you implement DJB2. So the way this is hashing is in an FMV1 format, from what I can see.
Yeah, so either way, it doesn't really matter which type of hash it's doing. Um, what matters is that you know that the hash is converting your key, your string, into a valid index in this array. Okay, so is that clear? So
Yeah,
every time you type the same exact key, it's going to give you the same exact index, right? And that's the goal here. And also, I wanted to point out, you can see a basic definition here, like it's a mathematical function, converts input into another numerical value. Okay, so, but what I wanted to point out was, it doesn't matter the length of what you put in, right? For example, it doesn't matter if you just send in one letter or 50 letters as the key, because the hash will always be the same size, right? And you can know the size based on the bits here, right? So uh, is that clear as well? Um, so yeah, another thing to point out is that the hash, either this one or the other one, doesn't matter. Uh, it can return, and it will return some value, um, probably bigger than your array size, like your storage size. So if you look at this, let me see, insert something here. Um, let me try to speed this up. You see, like it goes letter by letter and it continues changing the hash, right? But at the end, it still has to do another step that is crucial. Okay, so the final step is to cap it off at the maximum length of the storage. And what that means is, you see, like it gave me like a million or something, 12 million, anything, something weird. Okay, so it gave me a value. So I hashed the word animal, and it gave me like 1200 something, right? And this, of course, you don't have a storage with this amount of uh, slots, right? So you don't have an array with like 12 million indexes, right? So uh, what this means is that you have to cap it off, right? So say that the maximum is the size of your storage, right? So if the size of your storage is, I don't know, 10, right? It means that this value here will be reduced up until you get the rest. Okay, so let me see. So if you, yeah, 10 is easy because you can just delete everything and you get 3, right? So this will give me a rest of 3. I don't know if everyone is clear on this, but that will give me an index within the allowed um, space in storage. Okay, questions about this? Okay, so if your hash returns this huge number and then gets capped off, you'll get the index, the correct index, right? So, and then that's what this function is for, right? You call your hash and then you cap it off, okay? FNV1 is just you get an initial value, okay? You have a prime number as well. Both of these numbers, there's just arbitrary numbers from what I can tell. There's for sure some other mathematical reason for them, but it doesn't really matter here. Okay, so you basically go get them off the internet, and these are correct values. Okay, and then the goal of the hash is gonna create your number, right? So to do that, you're gonna go through every character in that key, right? And it's going to do some mathematical operation with that character's numerical value. Okay, is that clear? Same thing with DJV2. So it takes each character, does a mathematical operation with that character, and at the end, you'll have like every character on that key has changed the hash in a specific way. Okay. So that's pretty much it for hashes. Now, onto hash tables. So for your afternoon project, you have the minimum capacity here. And what I think we could do is have these 4 properties. And the first one would be size, or capacity is the same thing. Okay, so it's the size of your hash table, of your storage. Okay. And I made it so the default value is the minimum capacity, and I made sure it was an integer so it doesn't give you problems afterwards. All right. The storage, like I said before, it's just an array, and at the beginning it will be just filled with none, so it has nothing, but it does have the spaces, the spots there for you to fill in, right? And the spots are like this amount of spots that come in the capacity. All right. Then I have this. The full slots is supposed to keep track of how many of those spots in the storage are actually filled, or yeah, they're filled, right? How many are filled out of the total? Okay. This is just to calculate the load factor later on, okay? And like to be able to auto resize your table, you would have to know how many spots are full or not, so you can know like to reduce or to increase your table size, okay? And the resizing is also for that same purpose. So when you are resizing, you don't call more resize calls. Does that make okay? So any questions so far here with the init method? All right. So let me close these hashes and move on to get. Okay. So to get something from the hash table, the user will send you a key, which is basically the thing he wants to get from your table, right? It has a name, right? So first thing to do always is to figure out where that key is, right? And to do that, you need your index, because your storage is an array, right? Your storage is an array, so you need to know where exactly is that specific key. So you convert it to a number, and you get your number right here, your index, okay? Next, you get your current node. So this is already with linked lists, okay, but you just get the thing that is on that spot, right? Whatever is on that spot uh, related to this key, you get it, okay? And that would be pretty much it. If you didn't have linked lists, you just need two lines, like these first two lines here. So let me uncomment them. This would be it, right? If you didn't have linked lists, you basically would just get the index and return it, and there you go. You found the key, right? But because collisions happen, like here, right? Like this animal and banana key, right? Uh, this is where you have to deal with linked lists now, right? So I stored this first node here in a variable, and the goal is to search that linked list, right? So to do that, I just go through every node in the list, checking on each of them the key, all right? Whenever the key is equal to the node I'm on, right? So whenever I found the key, then this loop will stop because it no longer matches this condition right here, okay? And it will return the value of the node. So it will return, if I was searching for banana here, it will loop through, so first thing, right? You get the hash, right? The hash will give me number one, index one, right? Then I will search the list. It will loop. It will loop through animal. It's not the same key. It will loop to banana, and then he finds it. He finds it, right? And then it returns. Okay. So is everyone clear how you can get things from the hash table with linked lists and collision handling? Any questions? This is going to be fast if there's no questions. So next one, right? Let's add things. So the put is kind of an insert, right? Add stuff to the table, right? So again, like the easy version would be just getting your index and storing it there on the array on that spot, right? And that's without handling collisions. But when you do have to deal with them, there's a different problem, right? So if you look at, I'm just going to use this banana and the animal again every time, right? So if you look at this, when I inserted the banana here, right, it went to the number, the index one here, and it found this node, the first node animal, but it didn't override it, right? It needs to add it to the next, right? So it increased the list size here, okay? So this is exactly what we do, right? So first thing to know is the current node, so is this spot none, right? Does it have anything? If it doesn't have anything, right, then we just create a new node right there. So we just would create like this FFFF, right? It just creates a node there instead of none, okay? So, and there we go. We have a new full slot, right? So increase the load factor here, and this is for later, okay? Then, of course, if there's already something there, like in the animal case and the banana, right? You would go down here, and this is where the magic happens, right? So first thing you need to do is go to the end of that list. So basically, sorry, no, not to the end. loop through the list until you find the same key, right? So this key right here coming in, right? You're adding a new thing, right? So this key right here, you're gonna loop through the list until you find it, right? And what usually happens is that there is no uh, there is there is no key equal to that key because it's supposed to be a new one. But if there is, it will stop there, right? Because if there is, what you would do is replace that value with a new value, because you just said like the key animal equals 1, right? And then you would do it again, like put animal and then number 2 instead. And in that case, it does have to go to the animal and change just the value. So this is what the if statement is doing, right? If my node that I'm on right now is the same one that I'm trying to add, right? Then we just change the value, right? Because that it's not a new one, right? It's just the same one. We just want to update it, okay? But in the case that the key is a new key, so it's not found here in the loop, in that case, what will happen is that basically that loop will go to the end of the list because it never finds the key, so it keeps going until the end, right? And in that case, if you're at the last node, then the next node will be the new node. Okay, so any questions about this put method? Everyone is very quiet.
Where is the new node created in line 73?
Yes, line 70. So this is I made it very specific, right? This is a singly linked list node. Okay, so it's just the usual node. It has a key and the value and the next. Okay, so just has this, and yeah, I'm creating it right here and storing it in a variable, so it's easier to deal with it later on in the code. Okay, is that it?
Yeah, why the new node in the? Can you go back to the graph? Why the new node is not created in after banana?
Well,
And
it is.
it is spotted in number 2. You said that the new node is come in number 2, but we not see it after
Yeah, but
banana.
the thing here is that you can't see, like there's no key value pair. There's only the key. Okay. So what I was trying to say, let me see if I can draw here, right? If you have the key is the letters here, and the value was like 1. But if you try to add again, animal, and then the value is 2, right? The goal here is not to add another square here, right? The goal is to update the value to number 2, right? So that's what you have to keep in mind with this, right? With this part here, right? If the node, the thing is like this loop right here, right? It either stops at that key or it stops at the end of the list, right? So if it did stop at the key, you need to check for it and only change the value. But if it didn't stop at the key, then there is no key. Like it's at the end of the list. It's already looked for everywhere, right? It's already tried. So there's no other key like that. So it's a new one. So it means that you're at the end. This is the end of the list, and the next node is of course the new node then. Okay, so hope that's clear.
Yeah, thank
um,
you, Marky. Thank you.
all right, so Is that it? Any other questions? All right. So let's go to the delete then. What's going on here? Remove this. Okay. Okay. So I'm going to start with the basic example again. So if we didn't have linked lists and collision handling, we would just need these two lines. So getting the index and replacing whatever is on that spot with none. So we deleted it. It's empty now, right? And that would be it, right? The thing is that when you have linked lists, you have multiple values in a single index, right? So you can't just you can't just assign an index to none because it will delete the whole list, right? It doesn't make sense, right? So in that case, what you do need to do is, again, looping over the list, like in the put method. In the put method, you were trying to add something. Here, you're trying to delete something. So you're still going to check if the key has been found, right? So you're going to loop over the list. And while the key is not found, you'll continue going forward. Whenever this loop stops is either the case of it found that key or is at the end of the list again, right? So it's the same code, same exact functionality. Okay, so in the case that the key was not found, then my current node will be none because I'll be at the end of the list, right? So return nothing. In the case that it was found, okay, there's also two different things to consider here. Okay, so in the case that we find the key, first thing to do is to consider, like, if I had just one node that, like this dog here on index 8, if I have this case here where I'm trying to delete this node here, the goal is for it to be none now. Okay, so I don't know if that made sense. So if the node, so if the thing that you're trying to delete is also the first thing on that list, right, is also the first node on the list, you have to skip it, right? You have to skip it. So the thing with that is that, for example, on index 4, I have this DDDD, right? And I want to delete this one, right? And to do that, I would have to reassign, right? Yeah, I'll have to reassign this value right here of the index 4 to the other node right there, the second one, right? So I'm basically, I would never be able to access this node again, right? But that's the goal. We want to delete it, right? So that's what I'm doing here in this first if, right? So if the previous node is none, what does that mean, right? This is from the previous loop right here, right? So this loop is going to go through the lists. But like I said, if it finds the key that you're trying to delete, it stops. And that is the case that when the first node is already the key that you want to delete, then you wouldn't have a previous node. It's already the first node, okay? Does that make sense? So if there is no previous node, then the thing you want to delete is the first node, okay? Does that make sense? So just to reiterate, here on the storage, you're gonna reassign it to the current one dot next, right? So you're basically, if you have these nodes right here, 1, 2, and 3, right? And the 1 is obviously the first node, okay? So you're gonna say that this index on the storage is no longer gonna point to the node one. It's gonna point to one dot next, which is two, right? So it's the rest of the list. Okay, so you're basically deleting this part, and that's what this does. Okay. So everyone clear so far at this first half?
Okay. In line 97, we defined that previous node is current node.
Mm-hmm.
But in line 95, we say that previous node is none.
Yes.
So none cannot be current node unless if the previous node is updated in this while loop.
This is just an initial value, right? This is a variable. Okay, so while the loop is running, it will continuously change the previous node variable to be always the previous node than the one that the loop is on. Does that make sense? So it doesn't matter that this is none here. This is just so you would be able to, yeah, it kind of makes sense. So you'd be able to know that if you're on that first node of the list, then there is no previous node, so it's none, right? It doesn't have anything before that, right? So that's the goal here, right? You start out at none, but when the loop runs and eventually ends, you will get that previous node wherever of wherever position it stopped, right? So it doesn't matter, right? What matters is that if the previous node is none, then the loop didn't even run, right? It didn't even run, so it was right at the first node, so you found it right away. And the goal here is to skip that node so you connect it to the current dot next, right? So that's it. You skip the first node. Okay.
And in line, yeah, thank you. And in line 108, are we decreasing the array, the slots?
Yes.
This is the point of meaning.
Maybe it might not be exactly correct. It could be correct if I did this. So if the goal here is just to keep track of how many spots are full, okay, and it does make sense that I would need this condition right here to test that, because in the case that there is one node only, my current node.next will be none, right? So that's where it actually decreases the full slots, and otherwise it doesn't, because if I delete the animal node here, I'd still have the banana, and it wouldn't need to decrease because the slot is still full there. And yeah, that makes sense. It was missing something here. All right. So yeah, the second part is the one that yeah, it's a bit different, right? So in the case that the node that we were looking for to delete was not the first node, then this is where we are going to use our previous node variable, because now we know that we're going to have something like this: 1, 2, 3. But now instead of deleting 1, we want to delete the node 2, right? And in that case, you'd still have the 1 as the previous node now, right? You have that, and the dot next is currently pointing to node 2, but you don't want it to do that. You want it to point to node 3 instead. So if 1 pointed to node 3, then node 2 would be inaccessible and therefore deleted, right? So that's what we are doing here. We're basically saying node 1 dot next is no longer the 2 is the 3. Like it does dot next, right? It goes 2 nodes forwards, right? So yeah, it skips a node. And basically on this first part here, we're skipping the first node, but on the second part, we're skipping any given order node, right? Okay. And this is why we need this distinction between the previous node being none and the one being not none, right? Because you need to know if you're actually deleting, you need to know where you're deleting from, right? So yeah. Questions, concerns. Everyone good with deletes? So we've done get, put, and delete now. The rest would be the resize and the load factors. So with any problem, you'll find out that you don't wanna, like, you don't know how much data your hash table is gonna need, right? When you create a dictionary, you're not concerned about telling it, oh, I just want to have 8 keys on that maximum, right? Or yes, 5 minimum or something like that, right? So the goal with resizing and knowing the load factor is for your hash table to be able to manage itself, right? It manages itself. So what does that mean? So if I have number 5 of size, right? 5 spots, and I have 4 full slots, right? What do you think is the probability of collision when I add something new, right? Because I already have 4 of them full, right? So when you get that many spots full, there is a very high probability of collision, right? And you don't want to have a collision because collision is expensive. So if you look at put or delete or any of them, you see that anywhere you go where you have to deal with a linked list, you have to make a loop to find the thing, delete the thing, or place the new thing, right? So you have to make a loop, and that's not as efficient as O of 1. It's O of n or half or something, right? So does that make sense? So the thing with that, managing the amount of full spots and empty spots automatically is that it will decrease the probability of collision, and therefore your hash table is faster because it has to loop less times every time it has to do anything. Okay, made sense? So yeah, the way to do that, so let's go to the load factor here, is simple math, right? If you have 4 out of 5, then you have 80% full hash table. Does that make, it's just simple mathematics, right? So that's why we keep track of full slots or full indexes in the array. And we keep track of the size of the table, right? The total size. And yeah, this is just a division, right? So you get a percent, kind of a percentage. You're going to get either like 0.8, 0.5, something like that, right? And this is the easy one, right? And then you have the resize. So can anyone tell me why, like, what do you have to do to resize a hash table? I'm sure you already the code, but yeah, just try to get a stab at it.
I think you may want to resize if For example, you're trying to put in another key into a particular index, but there is no space whatsoever. The whole list or array is filled up. So you need to create an extra space for the new key that you want to bring in.
Okay, exactly. So how would you know that, right? How would you know that your table is full, right? You need to get your load factor, right? So if, let's see, if the current load is less than 20%, so our hash table has too few things, and our new size coming in is still more or equal to the minimum capacity, because there's that constraint there of minimum of 8, right? We're gonna just cut it in half, right? So we had like, I don't know, 18 size, but we only have like 2 items there. It doesn't matter, like just cut it to 9, because it doesn't need to be that large, right? And yeah, just wasted memory. Okay, so there we go. You return the new size there and you cut it in half. And like you said, if it's getting too full, right? So here I just chose 70%, right? So this is kind of arbitrary. You could say 80, but the sooner you double it, the better chance, the lower chances of collisions you get, right? Of course, you don't want to do it too soon as well, but yeah. I just chose 70%, and if the load is more than that, then we're going to double the size of the hash table, right? In any other cases, just don't do anything, okay? But yeah, that's it, right? So obviously, so not obviously, sorry. The reasoning behind what I did here was to put it in the input insert method, right? So I know that every time I try to add something, my table will get fuller, right? So I'm gonna check for each time I add something. I'm gonna check. I'm gonna try to resize it, but it's only gonna resize if this function down here that I showed you returns a new size, not the same, right? Does that make sense? So basically, this resize function starts out with a very simple condition, right? If it's not currently resizing the table and our new capacity is not 0, so we have a new one, we have a new size to actually go to, right? Then we're gonna start resizing. So this is like a Boolean flag so you know that you cannot call resize again while this one is running, okay? Then we're gonna store all the data that we had previously, okay? Before we mess it up, we just store it in a variable. So we have this array right here with all data. Update the size, create a new empty storage now, and the slots are all 0, okay? So now is the key part of resizing, like why do we have to do this second part here? Basically, what I'm asking is, why do you think I needed to store the old data and completely empty out the storage to have it with the new capacity there?
I think it is because when you increase the size, the index of certain keys and elements in the list will change, right?
Exactly. Our hash depends on the capacity, so on the size of the table, right? Remember up here on the hash index, right? Right here. This number right here is being capped by the actual full size of the table, right? So if before the table had 18 of size and now it's 9, we can't have stuff going into index 14 or 15, right? It doesn't make any sense. The array doesn't have space there. It doesn't have those indexes, okay? So what that means is basically you have to rehash everything and place everything again in the table when you resize it, okay? And to do that, we do for loops and while loops, right? So what I'm doing here is creating an initial loop. So this loop goes through the array, one index by index, right? And each one of those things will be either a node or a none value, right? It's either a node of the linked list or nothing is there, right? But when we do find the lists, we want to insert all of the lists, right? So we kind of have to do another loop for that because we need to go into the list and loop the lists itself and not the array, but the linked lists, right? Does that make sense? So each node of that list will be placed, so it will be inserted by using the same method we already have, right? So we don't need to code it again. So we can just call put again, and it will just do anything that he has to do. But we've already updated, right? We have already updated our hash table properties. So then it's gonna put, but it's gonna do it with the new size, the new hashes, also the new storage. Okay, so it's gonna do everything again, like from the beginning and automatically. All right. And of course, when we stop resizing, we've inserted everything that we have. We just say that we're not resizing anymore. Okay, so we can resize later on. Okay. Any questions about how a hash table can manage itself by resizing? Yeah, just this is pretty much it for hash tables. There's really not much more functionality we can try adding, but yeah, questions about this resize, load factor, or any of those other methods. All right. Well, if there's no question, go ahead.
Sorry. You said that there is in your explanation that it takes the resize takes the first condition on line 155. If current load is less than 0.20%, or the current shelf size is greater than the minimum capacity. The second condition,
yes,
where it takes place in the resize?
so
are we checking out it?
Okay, so this first if is checking, is my hash table too empty? Like, is it too large for the data that he has right now? If that's the case, just cut it in half, right? Just resize it to be smaller, right? And this case is the opposite. So if my hash table has too many items for the size that he has, then there's probably also a high probability of collision, right? So that's a very important one to resize now as fast as possible, right? So um, if that's the case, also resize, but double the size of the table, okay, instead of having it. So yeah, and what I do here is call this function, and this function called new size will return that number of the new size, right? And that's the argument for your resize. Your resize takes in the new capacity, right? The new size of the table itself. And yeah, I had to do it like this because of the tests. The tests are sending in parameters to resize. But you could do it directly in the resize function. You could do those conditions right there, and you wouldn't need to have like a separate thing there, because yeah, it's just really not required. You could just do this, right? Like if like this, or like if any of these happen, we could resize now, or I don't know, you could just do anything basically. You wouldn't need a separate function. So yeah. Was that
Yeah, yeah, thank you.
was that it?
Yeah, thank you.
Any other questions?
Thank
Okay. If there are questions later on, you can still send them to us. But yeah, I'll stop sharing my screen and pass on to Victor. So
All right.
yeah, go ahead.
Okay. Yeah. So to finish off, let's just solve a few problems using hash tables. And one thing you should understand, right, is in practice, you wouldn't really be creating your own hash tables from scratch, because dictionaries in Python or objects in JavaScript, they are already kind of hash table implementations, right? So, and they are really efficient, and they've been worked on for many years by lots of smart people. So that's kind of what you want to use instead of your own implementation, right? So let's see. Let's have a few problems with hash tables. Just share my screen now. Okay. So I'm not sure if you guys are familiar with LeetCode. It's like a website where you have lots of questions, code challenges that you can solve, and that kind of what I use in interviews. So if in most interviews, you'll probably be faced with like LeetCode questions or hackathon. So let's just check LeetCode and pick one of their hash table questions. I'm sure this is not opening. Yeah, I'm not sure what's going on. It doesn't want to open. Okay. So they have like a ton of problems and like different categories, and you have like the difficulty level and how many people have solved it. So for this particular first question, it's got to some, and 45% of people that tried it solved it, and it's quite easy. So let's actually try solving it. And it's a question on hash tables, right? So the problem is you have an array of integers like this, like a list of integers, and you have a target. So you have to return the two numbers that add up to give you that target. It's kind of a simple description. So you have a list, you have a target, and to return the two numbers that add up to give that target. Does anyone have any ideas on how to approach it? It doesn't have to be efficient or anything, just a random idea.
I think maybe what we want to do is we want to look through that list. We'll
Okay.
look through the list and get the individual, what's it called? The individual item, and we'll look, when we look through it, we'll get the individual item, and when we get each item, we want to add that item to its next item. I don't
Okay.
know, yeah, something like that. So if the next item, if the sum of the individual item we get and its next equals our target,
Okay.
that means we are on the right track.
Yeah,
Else,
sure.
if
What
we
if they're not next to each other?
Yeah. So what we are saying about today, right, is you have this. So we start from 2, we check 2, and the next name was 7, and we check. In this case, is we go on to 7, we check 7 and 11, and we go on to 11, check 11 and 15. What if it's 11 and 2? Checking just the next name, but doesn't account for that. So with your own approach, I think what you might mean is we look through the first time, and then we have, like, once we're on to for our first iteration, we have another loop inside that now sums up to each element that is left, and we check if it adds up to the target. That's what you mean. So yeah, let's try implementing that and let's evaluate if it's kind of what we want. So we have the first general loop. So like for each index in range, length of the input is norms. I comment here. Loop. So now we now need an inner loop for comparisons. So let's look for I remember for this our inner loop, we want to, if you want to compare with everything after 2, if you're on 7, not compare with everything after 7. So we do, so j goes from I plus 1 to the end. So for j in range, I plus 1, and so very simply, we just check if they add up to the target. So if norms I plus norms j um, equals to target, then it may be found what we're looking for. So we return a tuple of I and j, or an array of I and j. And yeah, and we know for sure there's a solution because we see that each input would have exactly one solution. So we don't have to handle any other case. So now, like, this is a very good first pass solution. And let's see if it runs, not just if it's feasible. Yes, it's accepted. So does anyone know, like, the runtime for this or potential problems that might arise with this? Let me just zoom in a little bit. It's like the runtime. So remember, we have this outer loop and we have this inner loop here.
I think this is quadratic.
So yeah, so this is n squared, right? So it means for each index, you have to loop for the entire array again. So this is big of n. The outer one is big of n, and this inner one is also big of n, because it depends on the length of the array, and then since they're nested, you multiply, and that's big of n squared. So yeah, that's a possible solution. But of course, you can always improve this. Because big of n squared is not always the best, and as things get bigger, it really begins to get slower. So yeah, we can reduce this to big of n, just a single iteration. Any ideas on how we can do that? All right, so with hash tables, remember, whenever you want to optimize, the first thing you should think about is hash tables, because they're used so much in algorithms, and because of one particular feature, they have like constant lookups. So that's like a very big thing about hash tables, like constant time lookup. So let's take advantage of that and let's improve this solution. So let me comment this out. Like I said, for our hash table, we can just use a regular dictionary in Python. So now let's think of how we can use the hash table to improve our solution. So let's start from 2. We know we start from 2, our target is 9. What do we have left? Or what should we add to 2 to form 9? That's 7, right? So we check our hash table. If 7 is there, 7 is not. That means we haven't seen 7 before. So we go on and we add 2 to our hash table. So now let's just do the regular set for now. So we start from 2. We know we need 7 to form 9. We check if 7 is in our set. It's not, so we add 2 to our set since we've seen it. So we want to sort things we've seen inside our sets. So we go on to 7. What do we need to form the targets? We need 2. Then here we know we've seen 2 already. So definitely that's, I know this is a bad example because it's too easy. Let me just pick a more complex example. So let's assume nums is 1, 5, let's say 6, let's say 3, and the target is 9. Target is 9. So now let's start again with our empty sets. We start from 1. So to get 9 from 1, we need 8. We check our sets. We haven't seen 8 before. So we add the one that we've seen already. So we add the one that we've seen. Then we go on to the next index, that's 5. What do we need to add to 5 to form the target? We need 4. We check our set. We haven't seen 4 yet. So now we add 5 that we've seen. We add 5 that we've seen. We go on to 6. What do we need to form the target? We need 3. We haven't seen 3 in our set before. So we add 6 that we just saw. And now for the final one, we go to 3. We need 6 to get to our target. And now we check our sets. We've already seen 6 before. Then it means for sure that's like the end. But now for this particular problem, we need to return the indices. So returning the sets, we have to use the dictionary so that we can also track the indices. Because with this, we only know for sure that we've seen 6. We don't know where 6 was in the array. So it means we still have to now start searching for 6 again. And that's bad. So we can just convert this to like a dictionary. And then we can store the index and the value as the value pairs. And that works quite well. So do you guys get how this particular algorithm works? Or do you want me to go right again?
Please go right again.
Okay. So let me use this example again. And you know what? Let me use an actual dictionary this time instead of a set. So we have our dictionary. So remember, what we want to turn our dictionary are things we've seen. So that once we are storing things we've seen, we're able to more easily find numbers that sum up to the target because we don't have to check twice. We are checking once, and once we see something, we store it somewhere. So whenever I want to confirm, we just check if we've seen it before, and it's really easy. So now this is the example. We have this input array. It has 1, 5, 6, 3, and our target is 9. And we have to find the 2 numbers that sum up to 9 and return their index or their indices. All right. So, okay, so we start from 1. What do we need to add to 1 to form 9? We need 8. So check our dictionary if we've seen 8 before. It's currently empty, so we've clearly not seen 8. So now we add 1 that we've seen because this dictionary tracks things we've seen. So now once we are done with 1, we add 1 to our dictionary. But now we won't track the index because that's what we are returning. So let's make the index the key and the value the value. So at index 0, we've seen 1. So let's go on to the next one. 5.
Sorry, maybe the other way around, so you can look up the number, right?
Yeah. I wasn't really I wasn't really particular about the order, just trying to but yeah, let's go with that. So let's go to the next one, 5. What do we need to add to 5 to form 9? We need 4. So we check our dictionary if 4 is there. Since 4 is in there, it means we've seen it, and we go to the next one. So let's add 5 to our dictionary. So 5 is the value, and the index, which is 1, because 5 is the index 1. So we go on to the next one, 6. What do we need to add to 6 to form 9? That's the target. We need 3. We check our dictionary if we've seen 3 before. We haven't seen 3, so we add 6. So 6 and 2. And now finally, last one, 3. What do we need to add to 3 to form our targets? We need 6. So we check our dictionary. We've seen 6 before. That's what we saw last. So then very easily, we know that we've seen the sum of values that form the targets. And once we return the indices, so we just return 2 and the index of this, which is also 3. And that's where it ends. So the reason why we are storing our index in our dictionary is because once you return the index, not the value for the algorithm. Does that make some sense? Fortunately, did that help?
Yes, it does. Yes, it does.
Okay.
Yes.
Hopefully, when we implement it, it would be a bit clearer. So let's try implementing this now. So we have our hash table, which is an empty dictionary by default. And now we need just one loop this time. So let's loop. And remember, there's this trick in Python. If you want to extract both the index and the value from a loop, you can use this enumerate thing. Let's show you. Enumerate Python. Okay. Okay, so you see, if we have this as our original array, we have bread, milk, and butter. If we do for item in enumerate grocery and we print item, what gets printed out is the index and then the value. So bread is index 0, so 0, comma bread. Milk is index 1, 1, comma milk, and butter is index 2, so 2, comma butter. So that's like a trick we can use for this. So we can do item in enumerate nums. And remember, this item is a tuple of like the index and the value. So we can just structure that here. So we can just do I, comma value in enumerate nums. So now for each number, remember the first thing we do is to find the complements. So for 2, we find the difference between 2 and target. So the number that you add to 2 that gives you the target. So that's what we do first. We first find the difference. So difference is the target minus the value, right? So once we find a target or difference, we check if it's in our hash table, if you've seen it before. So we just do if difference hash table. So if you've seen it before, it's actually very easy. Then we just return. Remember, we are returning the indices. So we return. Remember from our example, we're storing the index as the value and the actual number as the key. Yeah, so we can just do hash table difference I, which is this here. So once we've seen difference in our hash table before, we just return the index that we saw and current index, and that's where we end. But if not, we store it in our hash table. So if not, we just do hash table as this current value, as the key is the value equals to I. So yeah, that's pretty much it, I think. Yeah. So we look through our norms. For each number, we find the difference that we need to make up the targets, and we check if that difference is in the hash table already. If it is, then we end it there. So we just return the index in the hash table and the current index. Or if not, we add the current value to our hash table with the value as the key and the index as the value. And that's it. So let's see if this passes. Yeah, so yeah, of course passes. So with this, so we have just a single for loop, nothing nested. And the only thing that might be suspicious is this line 15, because we're checking if difference in hash table. But if this was a list, this would be big of n. But since it's an object or a hash table, and that has constant pickup time, so this is constant time. That means no matter how big this gets, checking something is always constant time. So it's pretty efficient. So yeah, that's kind of how we solve this, and it's not too difficult. So do you guys understand that?
Yeah. But the runtime of the previous solution was 48 milliseconds.
Yeah,
That means that the processor ran it faster than this, even if it was a quadratic execution.
No, that's the website. It's different. Yeah, it depends.
yeah. So so it's network based, and even if it wasn't network based, if you look at this graph, not this graph. Wait, hold on. There's this graph that was really good in showing that. Let's see if I can find it. So like these differences come into play when things get larger. So like at the start, it might seem like, oh, the big of n squared is more efficient than the big of n. But as you increase the inputs, that's when you see like the vast improvements. Let's try to find the particular chart I saw that was quite explanatory. Yeah, I can't find it right now.
Either way, if
no,
you
I understand what you're saying. I'm saying that when we had the first solution, it was the runtime faster, but the time complexity was not good enough. And the second solution was larger, meaning that it had 4 milliseconds more, but the time complexity was constant. So my question was why we have this kind of difference,
I get
even
your point.
if the site was doing faster.
All right. So look at this chart, right? So this chart shows the time complexity, how it grows as the input grows. Now let's look at when the input is very small. Let's say at this particular point. If we trace it, so I'm just trying to annotate something here. So at this point, if we trace it up, right? So if you see where it crosses the big of n, it crosses the big of n at this point. It crosses constant time at this point. So from here, it might look like, oh, the big O of n is way faster than the constant time. But now let's check when the inputs get really big. So big O of 1 is still at that same point. But big O of n has grown from here and it's basically infinite, like so high. So thinking about time complexity is that at small inputs, it's very easy to be deceived and be like, it's not very impactful, but it doesn't matter. But when things get bigger, that's when you really see how things scale and like the importance of it. So you shouldn't be too concerned about small inputs, about how it affects it. Do you understand?
Yeah, I understand because you said it also, I think in the morning, or you explained somewhere that when the length of the array is too long, or when we have nested for loops inside, the time complexity changing. It's
Yeah.
not a constant. I understand that. My question that you explained to me, and I fully understand, was why we had those kind of small millisecond time. But okay, I fully understand. If you, Victor, thank you very much.
Yeah, but in this case, it's probably just the network. Something small.
I think when you do submit, it does more tests, and if you submit the first solution there, it won't. It will tell you that it's slow.
Yeah, let's try it. Let's try it. But I'm not sure this particular problem checks optimization, but let's try it. Because there's some problems on its code that check optimization, like how fast it runs. So let's try with the old one first. So this is faster than 5%. So it's quite slow. It's really slow. So now let's try the other one.
Took 7 seconds.
Yes, 7 to 8 milliseconds. Okay. So let's try the other one. So this is faster than 33%, and it took 92 milliseconds. Can you see how much? This is less than a second, and that was 7 seconds. So of course, they are testing with larger inputs, so it's easier to see the difference. I can try again. I'm surprised it wasn't faster. It's now 60. Well, anyway, yeah, that's just the point. It's a lot faster because it's big of n and it's big of n squared. So it really matters. All right. So now let's do something. Oh, sorry, we're going to do something.
Okay, I agree. I see the test.
Okay, awesome. So let's move on to something else. So let me just pick some of what you had to do yesterday and today and see if we can solve it together. 1 second. I'm just trying to find it. Okay. Okay. So this is the repo. I just scroll it down. So let's pick this one. Let's look up the question and let's see. All right. So can you guys see my screen? Okay.
Yes.
So here we have a function slope to slope that takes in two values x and y and does some computation and returns the value, and that's all this does. So down here we have the function being called, but it's being called 50,000 times, and the x and y are random values. So x is between 2 and 14, and y is between 3 and 6, and they both go into this. So you know what? Let's just run this and let's see what happens. Let's run this and let's see what happens. So yeah, see, this is after a few seconds. We are just at 100 and something, and I'm going up to 50,000. So it's really slow. This will probably take like an hour or if no more. So the question is, how can we optimize this to be fast? So there's a common pattern you can see. You can see x is always between 2 and 14, and y is always between 3 and 6. That means between 0 and 50,000, there'll be lots of repetitions. Like there'll be many cases where you are doing the same operation over and over and over and over. So whenever you notice that kind of pattern in a problem you're solving, then the first thing you should think about is like caching or memorization. And what that simply means is storing things you've already solved before. And whenever you resolve it, you just pick it from your storage. Right. So let's implement this. It shouldn't be so difficult, but let's implement it for this. Okay. So Remember, the cache is always a dictionary or something because of how efficient it is, constant lookup time. So we have a cache, which is an empty object by default. All right. So so our key in this case, our key will be a mix of X and Y because our key has to be unique to each solution, right? And the only thing that is unique to this particular solution is X and Y combined together as like a tuple or something. So let's use that. So what we can do is whenever we solve something, we add it to our cache. And when we see that same key again, we just pick it from the cache. So like I said, our key will be tuple X and Y. So now what we can do here is whenever we have a new X and Y, the first thing we do is to find the key. Then we check if our key is in the cache or if it's not in the cache, either way. So if key is not in our cache, we add it to our cache, similar to what we did for the previous problem. So we add it to our cache. So we just do cache key equals, let's just call this function assigning X and Y. So if key is not in the cache, we add it to our cache. And but if it's in our cache, we just return cache. So I'll go back again. Whenever we get a new key on X and Y, the first thing we do is we find or we make our key, which is a tuple of X and Y. Then we check if that key is in the cache. So if we've seen it before, we just return that particular thing in our cache. But if not, we add it to our cache and then we return it. So it's like a very simple optimization. But now let's see how much it improves our performance. Sorry, I didn't change. So let me just change this to slow phone instead. Yeah, it's not faster than expected. I was thinking it would be much faster than this.
It depends on the computer as well.
Yeah. But just because I have Zoom and some other thing. But
your computer is low, that's why.
No, let me try this again and see what's going on.
I mean, even in a few seconds, it reached 380, and the other one was like 100. So
Yeah, I guess. But yeah, that's what memorization does. Yeah, so you can see this is just it's still on 11, 15, 20. And let's change to our new implementation.
But if the computer plays an important role here, if the processor of the computer needs to be very fast, how will you know if the optimization of this exercise is the best?
Yeah, I mean, even with my own processor and everything, you can see that this is much faster than the old one because at this point it was still on maybe 20 or 30. So and because of how much the computer plays an impact on the speed of the algorithm, that's why we have big O notation. Because what big O notation is like computer agnostic. So it's like a way of representing the speed of your algorithms without taking into account your performance of your computer. So when you know something is big of n, it's always big of n. No matter how fast or how slow the computer is, it remains the same. If it's big of n squared, it's always big of n squared. Because with this now, if this runs and you say, oh, it runs in 5 seconds, on your computer, maybe 1 second, on a different computer, maybe 20 seconds. So it's not like a reliable metric. So that's why we use big notation. But anyway, with this problem, you can see with just a very simple caching, it has like increased our runtime by a lot, by a huge factor, in fact. So yeah, that's kind of what you have to do here.
Nice. Can you go through the expensive sequence?
Through what? Okay, expensive.
And explain it a little bit.
Yeah, so let's look at the reading first. So it says the expressive sequence is like a Fibonacci sequence, but a lot more intensive and a lot less useful. So x, y, z, if x is less than 0, it returns y plus z. But if x is bigger than 0, it returns expensive sequence x minus 1, comma y plus 1z plus this plus this plus this. Okay. So from here, it's very obvious to see that they're going to be doing lots of repeated work. So most likely you're going to be using caching or memoization to have any reasonable runtime from this. All right, so let's just write down the basic rules first.
My question is that if you go back to the README file, less than equal to 0 means if x is less than equal than 0. So I was thinking, what number is at the same time less than equal than 0? Less because the output.
It's less or. It's less or.
So if x minus 1, you should return y plus z. If x is 0, return y plus z.
Yeah, it's less or equal to 0, not both.
It's less, not at the same time. Because problem, I couldn't understand the mathematical point there. A number that is less and equal than 0 gives me x plus z.
All right, so let's implement this. So let's start with the regular way, right? So these are the conditions. So let's just do that here. So if x is less than or equal to 0, return y plus z.
Okay, I'm sorry to interrupt, but the reason why the lookup table was slow, if you go back there, it was because the cache declaration on line 20 is inside the function. So it keeps resetting the cache back to empty.
Yeah,
Just place it outside the function and it should work.
The price there was taking such a long time. Yeah, so
just
we are calling. Yeah. Oh, you know what? Yeah. Let's see if that helps. Okay.
You still need to change it down there. Yeah. So after the first few hundred, it should like go really fast. Yep.
Okay, of course. So yeah, what was happening was whenever we call this, we would empty out the cache and we initialize it to an empty object. So everything that we had stored there would get wiped out. So now that we have it outside, it's like it remains constant and we keep adding to it.
So the cache must be outside of the function in order to work faster.
I mean, it depends. It depends. If for some reason we had if this function wasn't being recalled at all, then it wouldn't matter if it's inside or outside. But in this case, since it's being recalled, with each recall, if this was inside here like it was before, so whenever this calls itself again, it assigns an empty object to cache again, and it clears everything that was there before. So we have to move it out. But if for some reason this wasn't being recalled, then we can have it inside here and to be fine.
Yeah, it's more a problem of the test itself. Like it's calling that for loop is calling the function like every time there's new numbers, right? So
it clears out the cache. Okay. Let's go with this. So if x is equal to 0, we return y plus z, else, than else, actually. So just return this. This is going to be really slow. Let's see. Yeah, it's really slow. It's already stuck. So yeah, I'll just stop it here. Yeah.
This is the solution of the problem.
This is like a bad solution because it's very slow.
Oh.
So you see how it was already stuck just very early. Now let's think of how we can optimize this. Of course, we're going to use a cache. Now this time, let's put it outside. It doesn't overwrite itself. So we have a cache. So what we want is, whenever we calculate a new expression sequence, we store it in our cache. And then whenever any subsequent time we are doing that same calculation, we just pick it from the cache. So yeah.
Can you explain it by an annotation how you will approach this problem, please?
Yeah, I mean, so like what I did, we have a first pass solution, which is just like the normal logical way that you approach it the first time. And then we try it and it's slow. It's not fast enough. So we want to improve the solution. So we know the reason why it's slow is because we are doing the same thing over and over and over again. And when you're doing the same thing over and over and over, how can you avoid that? You can avoid that by doing it just once and store it somewhere. And each time you want to do it again, just pick it from what you've stored, right? So, and whenever you are doing that, you need the cache, which is an empty object in this case. So now, if x is less than or equal to 0, return y plus z. This is pretty simple and it doesn't have to be improved. The problem lies here in this particular line. So instead of always returning and calculating this all the time, let's add an if check that checks if it's in the cache already. All right. So we do so let's make our key first. If we send the informal one, we made a key first that we use to track things. So remember, the key has to be unique to each instance or to each problem. So in this case, since we have x, y, z, we can make our key to be a tuple of those three variables. So let's make our key to be equals to x, y, z. So once we have our key, we can check if key is not in our cache. So if this is the first time we are solving this, that's the only time that we solve it. So if this is the first time we are solving it, then we solve it and then we store it in our cache. So cache equals to this. So it's very similar to this former one. If key is not in the cache, we solve it and we store it in our cache with that key. So that's the same thing we're doing here. If key is not in the cache, we solve it and we store it in our cache with that key. All right. And then we return. So you can see it's basically the same. It's the same concept, but it's different problems. So once you understand the concept of hash tables and caching and minimization, it's something that you use a lot in solving problems and optimizing your algorithms. So let's try running this and let's see what happens. So yeah, you see how fast it is. It's basically like a second. And with the former one, it stopped here. And the reason why is because imagine you're doing 1 + 1 like 100 times, or let's say you're doing 1 + 1 a million times. That's going to be slow. But if you do 1 + 1 once, you start somewhere. Whenever you hit again, you just return that. It's a lot faster. So that's the same concept we're applying here. We only calculate this when we have to. If not, we return it from our cache. And yeah, that's kind of the concept.
So first of all, we need to then define the cache that is empty. And then we need also to define the keys.
Yeah. So
the keys are unique.
Yeah, when I say unique, just some kind of combination that represents each solution. So for this particular solution, it depends on X, Y, and Z. So our key is just a combination of those three things. So just some kind of combination that represents the problem. So that's what we do here. And so if key is in the cache, we calculate it and then we store it in the cache and then return it. Or if key is in the cache, then this gets skipped over and then we just return it directly. So yeah, any questions about memorization of caching or hash tables generally?
So the problem was the methodology, how you approach each problem, but each problem has different kind of how say elements.
Yeah, it might seem that way, but once you understand the problem and once you break it down, like the major building blocks, then it's going to be very similar with something you've solved before. Because majority of the times, the problem is mostly about translating the sentences and the words you have on your screen. So like code in your head. Once you're able to pass that step, then it's going to be very simple. It's going to be very simple. So you see how similar this is with the lookup table, and how similar even this is with the lead code thing we solved earlier. So with this particular lead code thing, the key was our difference. It's like the very similar solution, but the key is different. And then we check if the key, let's just change the key so you can easier to understand. So we find our key first. We check if our key is in the hash table. If it is, then we just return it. But if not, we add it to our hash table. So you see, the problems we solve today, they're the same solution or the same implementation of very, very different questions. So that's how lots of things in coding work. That when you're able to drill them down, like basic blocks, they are very similar, even with how different they might look initially.
In the previous question that you explained in the VS Code, what will be the optimization time? Constant?
What would be the
the time complexity?
Yeah, I mean this is linear time. Yeah, I mean the only remember constant is only when the output doesn't depend on the inputs. But with this, as the inputs grows,
but the length of the array here, it's too short. Doesn't have it doesn't have any nested loop. You have only one condition. Can be described as a constant time, or it's
yeah, like I was saying, it's only constant time if like the output doesn't depend on the inputs, or if like so for constant time, if we have this kind of thing, so if we have let's assume we have def const, it takes in some list and we return list there. So in particular example, we know even if list is one element, let's assume list is just one, it would return one. If list goes from 1 up to 1,000,000, it will still return just 1. So in that case, this is the constant time algorithm, because no matter how this gets, no matter how big this gets, it doesn't really matter. You always return this. So it's constant time, it's constant work it does. But with like a linear time, it means as your input grows, yeah, most likely your runtime will grow. So if your input is 1, it does something. If your input is 5, what it does increases. If your input is 100, what it does increases. So that's like the most common runtime you probably face, because that's what is it affects lots of problems.
Yeah, that's exactly what you're doing with the cache. Like you're basically whenever something is already on the cache, it's O of 1, right? Because you've already solved it before, and that's the goal. How the more O of 1 operations, the faster it is.
A little faster than the previous one.
Thank you.
I have a question. From the expensive sequence I'm seeing here, like these numbers are shown here. I kind of did enjoy when you're kind of explaining it, but I guess from the last explanation you gave to Dinos, I was able to understand it, but I still don't understand the output of these numbers. How they like,
Okay, so
yeah.
this sequence, it takes in three numbers. It takes in x, y, and z. And if x is less than or equal to 0, all it does is that it returns y plus z. So if we call this with expensive, let's copy it. If we call this with, let's say, 0, 100, and 1,000, what this will return is just 100 plus 1,000 because x is equal to 0. But if x is more than 0, so if x was 5, what it now does is that it calls expensive sequence and passes in x minus 1, y plus 1, and z. Then plus, call this again, passing in this, plus, it calls this again, passing in this. So it means it keeps doing the same thing. So that further call would call this again, and that further call would call this again until x becomes 0, and then it starts compiling everything and adding it back up together. So it's just like a regular recursive algorithm. Do you understand?
I understand.
All right, great. So yeah, yeah, that's kind of I mean, we're almost out of time. So any questions, anything you're not clear on, or yeah, before we end this for today? I'm not okay. You want to say anything?
Yeah, regarding the last question, so the goal of the cache, right, is to catch those moments where you have X, Y, and Z, right, and they've already been solved. Like this function call has already been solved with those numbers, those specific numbers. So the goal is to return that number from cache instead of calling all of these operations again. Uh, I don't know if that's what you were asking about, Josiah, right?
Yeah, exactly. Yeah.
So those numbers are in the cache and we are calling them from the cache.
No,
That's what you said.
you're not calling them from the cache. You're calling the results based on the key, right? So because your key is based on the function arguments, right? You know that whenever the function is called with those specific numbers, because they are the key, right? It gives you that specific result, right? So you save it, and because you saved it, you won't have to ever again calculate or do anything else to get the value when that function is called with the exact same numbers again, which is what happens here a lot of times, like uh, a ton of times, like x. So for example, x, right, is being always doing like x minus 1, x minus 2, x minus 3, like how many repeated numbers, how many repeated calls do you think happen? Like it's always the same numbers. Like every time x increases, um, and other functions were called before it, right? So if x was 14, but you called the same exact function with the number 10 as x before, right? You would only need to solve like the 13, the 12, the 11, and the other 10 are in cache from the previous call, right? That's a ton of calls saved, right? So they're all saved. Their results are saved. So yeah, that's it.
Thank you.
And yeah, I don't have any other challenges per se or anything else to say here, unless there are questions or any other suggestions.
No, I'm okay. Thank you.
Yeah. In your free time, if you haven't tried some of these other ones, like this Markov one, because what it says is you have some input string, and from there, using a hash table, you try and form this kind of structure where you have each word in the input string and all possible things that can follow it. So here you have cats. The only thing that can follow cat is and. So we have and here. Now for and, this is the first and. We can have dogs. For and, we can have birds. And for and, we can have fish. So here we have and, we have dogs, birds, fish. So now dogs, for dogs, you can have and for dogs here, you can have birds. So you have and birds. For birds, you can have and for fish, you can have dogs. So once you form this kind of structure, it's very easy to construct new sentences because you already have like kind of a mapping between words and what can follow it. So you can just say cats and then we go to and can be fish. So cats and fish. So it's like easy to make sentences from this kind of structure. So that's kind of what the Markov chain is. So what it says is you first read the inputs, and the input is just like a long string of lots of words. So it says first read the inputs and split it, then analyze it and build up your data set, which is this. So you build this thing up when in dictionary. And once you build it, you just pick a start word, and then you loop through, and then you make like a random sentence. So it's like lots of fun. And if you have the time, try and solve it and see how far you're able to move with it.
Thank you,
All right.
Victor.
Yeah. So
And if you want to waste 10 hours, go to some diff. That's a pretty hard one.
which one? Oh, some diff. Okay.
Some diff. The best I could do was OFN to the power of 4. So yeah.
Yeah, there are lots of fun problems here. So if you have time over the weekend, just try and take a stab at some of them and then see how far you're able to go with it. All right. So yeah, thank you for coming today. Yeah, and good luck in your sprint tomorrow.
Thank you guys for the explanation. It was very useful. You've done a great job. You gave us some boost confidence for tomorrow before we all cry.
Thank you, Victor. Thank you, Ned.
Thank you.
Yeah.
Thank you, Melky. Thank you, Elvis. Thank you, Victor.
All right. I'll post the recording as soon as possible, and I'll see you all tomorrow. Yeah.
Yeah. Thank you. Bye-bye.